So today we're going to talk about Gibbs phase rule, and really we're not going to prove it. We're just going to talk about its use and its definition, basically. And we're actually going to prove it in a future screencast. But for now, let's just use it. So let me write out Gibbs phase rule first. F is equal to the number of components minus the number of phases plus 2. So this is degrees of freedom. And degrees of freedom is just the number of leftover variables. So how much variance is in the system? This is just, C is the number of components. So how many separate chemicals are in the system? Phi, you could think of, it's the phi, it's like a Greek P, is the number of phases, the Greek pH, right? The number of phases. Okay? So let's talk about how we could use Gibbs phase rule. Let's imagine we have a situation like this. Let's look at the triple point here. Well, if we were to look at that triple point, we could say, okay, how many components and phases are present? Well, for this chapter, C is really easy. We're talking about one component phase diagram, so there's only one component. How many phases are present there? Well, we've got the liquid, we've got the gas, we've got the solids, we've got 3 phases. And so we've got 3 minus 3 is equal to 0. There's no degrees of freedom. All right, and we actually can see that just by looking at the phase diagram, right? If we want to have all 3 phases in equilibrium, there's only one pressure and one temperature where that's going to happen. We don't get to choose any variables. On the other hand, if we were to look at, say, here, where we have solid and liquid in equilibrium, actually we got to be careful, we're above the critical pressure, so we should say solid and supercritical fluid in equilibrium. Well, we've got Gibbs phase rule out here. Well, we've got one component, we've only got 2 phases, so we end up with degrees of freedom as 1. We get to choose one variable. What that means in practice is we can choose a temperature, but then the pressure is given for us, right? If we want to have the 2 things in equilibrium, we only get to choose temperature or pressure. The other variable will be chosen for us. So that's 1 degree of freedom. On the other hand, if I'm over here, just pick a spot at random, we could say degrees of freedom, well, there's 1 component, there's only 1 phase, so we end up with 3 minus 1 is equal to 2, which means that we can actually choose our temperature or our pressure, and we can vary both of them and still have 1 phase present. So that's how to use Gibbs phase rule. And this will become even more important when we start looking at multiple component phase diagrams